Algebra 2, Chapter 4, Section 2, Functions and Expressions. First, let's start by doing some graphing. We're going to be doing some graphing in this class, so let's review what we need to do to make a graph by working the following example. This example says, graph the function t of r is 400 over r, or let the t of r be 400 over r, by making a table for the values given here. So let's start by making the table. So we have the input r, we have the output t of r. So let's make a table. R, we're told we should use these values: 25, 80, 100, 200, and 400. So the output will be 400 over 25, which is 16, 400 over 80, which is 5, 400 over 100, which is 4, 400 over 200, which is 2, and 400 over 400, which is 1. So we have some inputs and some outputs. So whenever we're doing a graph, we need to define an origin, the point that's the starting point. We should define axes and label them. This is the r-axis, and this is the t of r-axis, or the output axis. Let's try to make it a little straighter. We can use graph paper when graphing to get better results. Maybe I'll do an example on graph paper at some point here. But today we're going to just do it freestyle. So we have t of r on one axis and r on the other. Now we need to give some sense of scale. So we need to go from 0 here at the origin to 400 on the input axis, the r-axis. So we'll go ahead and put a tick at 400, one at 200, one at 100, one at 80. And using graph paper, we can make the graph divisions, nice divisions of these numbers. One at 1/4 of 100 of 25. And on the output axis, we need to go from 16, and it's easy to divide things in half here, all the way down to 1. And we should probably go ahead and put 5 on here, just since we have it here. Okay, and a ruler will also help graph, and I can't really use a ruler against the computer very easily. So let's just freewheel here with this crooked axis. So we'll have 25 and 16 as one of our points on our graph. So now we're going to place points. Let's use a different color for this. Blue points. Okay, 25, 80 we have 5. At 100 we had 4. At 200 we had 2. And at 400 we had 1. Sorry, at 25 we didn't have 8, we had 16. Make sure we fill the table in correctly. So now if we connect the dots sort of with a line, we can sketch our graph. So we'll come down and connect the dots with a rough line. We get this shape. If you want to know what this shape is called, it's called a hyperbola. We'll talk more about that much later in the course. But we now have a graph. So the key things in a graph are axes. The axes need to be perpendicular. This is so you can define an input and an output that are independent of each other. You also need to define, you need to label things. So you need to label the axes that are input and output with their corresponding labels so that you can understand what they are. You need to give a sense of scale. And you can do this with tick marks, or if you're using graph paper, you can say, 1 square equals 1 unit. You don't even have to put that here. You could just write that somewhere so that the sense of scale is known. And then you just need to plot the points and draw. So any function can be graphed. Actually, lots of things can be graphed, not just functions, by putting points on that correspond with pairs of input output. Okay, so a function, we have inputs and outputs. So we have these pairs. We can use these pairs to write points. And then we can connect the points if we want to sort of guess at what the function looks at. If we want a very accurate view, we could fill in a table that goes from 0 to 400 by values of 1. 0, 1, 2, 3, 4, 5. And of course this would take a very long time. But if you spent the time to do it, you would end up with a very accurate version of the function, especially using a ruler and graph paper. Now, it's essentially what a graphing calculator or a graphing program on your computer will do to make a graph. It will do exactly what I said. It will plug in lots of numbers for R. Computers are great at this. Evaluate the function and come up with an output, and it will draw all the points, and the resulting points look like a beautiful graph. Now I will go ahead and make a comment about that. When you are graphing on a calculator, if this may come up in the future, this may be helpful to know now, and you graph a function like 1 over, like this function, 400 over R, okay? The resulting graph on the calculator will look like this. You'll have this hyperbolic shape comes down, and you'll see this line coming up and coming back down. And this is because the graphing calculator makes a mistake in connecting the dots. It connects this dot with this dot, even though there's no connection here. There's no connection here because when R is 0, there is no output of the function. Okay, so R is not an allowed input. We're not allowed to put R in, because if we were, we would have not a function. Remember, we have to have one output, exactly one output for every input. So we'll talk more about that concept later. But if we go ahead and erase this, the correct view of the function would be no bridge, just lines here and here. And if you were to actually plot and put in points without connecting the lines, you would see that shape correctly. It's just a helpful thing to know. Functions sometimes have letters that are not variables, and these letters are constant with respect to the input. In other words, the value of the input, what we put in, will not affect the value of these constants. For instance, in this particular function, c is a constant. It's not listed as one of the inputs. Therefore, it does not vary with the input. In fact, this represents one of Einstein's equations. It's very famous. E equals mc squared. And the c here stands for the speed of light in vacuum, which is a physical constant. It doesn't change with mass or anything else for that matter. And in the book, such functions are often written as equations without function notation, and then he asks you about them as if they were functions. This is very confusing, so in the slides I will be sure to write them with function notation to help us keep track of what the input is. What about equivalent functions? You can have two functions that are equivalent, and the book will often just use the word same. Are these two functions the same? What it means by that is that they're equivalent. Two functions are equivalent if and only if their rules express equivalent operations. For instance, if I have a function whose black box rule is halve it, which means take it in half, and I have another function whose black box rule is multiply by 0.5. Those are equivalent. Those are the same function, or they're equivalent functions, because if I put in 2, I'll get out 1. And if I put in 2, I'll get out 1. Another way of thinking of equivalent functions is that for whatever you put in, you get the same thing out for both functions. And that's just another way of defining equivalence. Remember, equivalence for expressions means that they have the same values for all values of the variables. In this sense, the rule doesn't have a variable. It's a placeholder, so it's a little confusing, but all we need to do is show that this defines the same operations as this. To do that, we can show this expression is equivalent to this expression when using the same placeholder. So we can just remember, we can change the placeholder all we want in a function definition, and it will still be an equivalent function. It'll be the same function. So if I say, let's give G the same input letter, that'll help us out here. Okay, so here we have f of x is 2 times 0.1x. And we can show that 2 times 0.1x is equivalent to 0.2x using the distributive law. 2 times 0.1 is 0.2x. Okay, so that proves that it's the same for all values of the variables. So how about another example along those lines? Here let's say let g of a be a squared minus a. Which of the following pairs of expressions are equivalent? A, g of 2a and g of a. So we're asking, are these equivalent? Remember, to show it's equivalent, we need to think about the expression that defines its rule. So here we would have g of 2a. Let's go ahead and figure out what g of 2a would be. G of 2a would be putting in 2a for a. We'd have 2a squared minus 2a, which would be 4a squared minus 2a. And so if I put in the number 1 in the first expression for a, so if I put in 1 here, I'd have g of 2 times 1, or we'd have this expression. So here if we put in 1, we'd get out, if we put in 1, so we can just write this in English. If we put in 1, we get out 4 minus 2, which is 2. If we put to the first, so the first, if we put in 1, we get out 2. And the second, if we put in 1, we get out 0. 1 minus 1 is 0. Okay, another way of thinking of this is g of 2 does not equal g of 1. And so therefore these two things are not equivalent. Okay, and that's because if we put in 2, we get, again, 2, and if we put in 1, we get 0. These aren't the same. And so that's one counterexample. When a equals 1, g of 2 does not equal g of 1, therefore not equivalent. This 3 dots means therefore, like that. B, 1/2 g of a and g of a over 2. Well, here, I mean, it's the same thing we were just talking about. Multiplying by 1/2 is the same as dividing by 2. So they're equivalent. We can just write that out in English. Multiplying by 1/2 is equivalent to dividing by 2 by the rules of fractions, or multiplication, the rules of fractions. Okay, so that's the answer is yes, equivalent. C, well, we can remember we can show a counterexample, g of a plus 1 and g of a plus 1. So if we put in 0 for our input, in both cases, we'd have g of 0 plus 1, which would be g of 1, which would be 1 squared minus 1, which is 0. G of, we're putting in 0 for a. G of 0 plus 1, second expression, would be putting in 0, we get 0 squared minus 0, which is 0, plus 1 is 1. So those are not the same, because here we have, first one gave us 0, and the second one gave us 1. So the answer is no, they're not equal when a equals 0. Next, let's talk about how to put functions in a particular form. So if we're told to put a function in this form, we need to have our rules such that we can identify k, which must be a constant, it's not an input, and t the input. And we can have different kinds of forms for functions. Again, unfortunately, the book does not use function notation and doesn't put the t in the parenthesis next to the q to indicate q is a function of t, which is very confusing, and I'm sorry about that. But it's just the fact of how we often have confusing notations in math. Here it's kind of assumed that you recognize k as a constant and t as the variable. I like to make that explicit. So we need to put this rule into this form, k of t, to get our function in that form. So q of t would then be, by thinking about the distributive law, we can use factoring here to pull the t out. And remember, you can either think of pulling t in front or pulling the t in the back. I often like to think of pulling it in the back because the order of operations doesn't change. If I distribute this back out, I get back what I started with without swapping orders of things. And here we have the k above and the t. Now we're not done. If the problem had said, let's pretend the problem said identify k, so that we can identify it. So let's say k is 5 plus r. Let's pretend the problem said that, because that often it will, and if you forget to put that, you won't get full credit. You need to follow the instructions in the problem. B, we need to put q of t in this form, constant times t. Here we can rewrite or regroup the division into a fraction and the negative together, and we get that k is minus 1/10. For C, much more complicated. We have q of t as this crazy expression, which doesn't even look like it can possibly be in this form. Well, let's go ahead and distribute this out and see what happens. Maybe we'll have some canceling. T squared plus t is the first expression, minus t squared plus t, because we have minus times minus. Sure enough, t squared minus t squared is 0. We're left with 2t, k is 2. So here the problem really was massaging the crazy expression into the form that we need it to be in.